Hi students, and welcome to a continuation of Chapter 7 and 8 combination chapter, looking at the different types of bonds that molecules can participate in. We have been taking time to learn how to draw Lewis structures to represent covalent molecules. So these are molecules that are held together by that share, remember, fight to the death, share, that those molecules both grab on to a valence electron and both try to pull it to their own side, creating this kind of locked in bond. Once that happens, there are some consequences for the atom, and we call these consequences intermolecular forces. So an intermolecular force is an emergent property. This is a behavior that emerges based on the foundations or the way that the molecule is put together. So this is something that maybe would be not totally predictable if you didn't know it was going to happen. But once we see them, we can use these intermolecular forces to explain why one particular molecule behaves one way, where another molecule maybe behaves a different way. And so we're going to be looking at these forces, that a way that different molecules interact within a solution when they come into contact. So it's important right now to distinguish intermolecular forces from intramolecular forces. So an intramolecular force is within the molecule. So an intramolecular force would be something like a covalent or ionic bond. These are intramolecular forces. Intermolecular forces is between. And I know this sounds really weird. I think that when we just hear it on its own, we tend to think like inside, inside. But that's not the case. Think of terms like interaction or international. Maybe you're thinking of another word, but an interaction is between an action between two people. During COVID time, we are missing interaction because we're not seeing any other people. You can't interact if you're by yourself. International is a flight that goes between two countries. You can't go on an international flight within your own country. That's not international. You need two countries to do an international flight. So when we talk about an intermolecular force, you need two molecules to make it happen. An intermolecular force is an interaction between two or more molecules. So these are behaviors that one molecule exhibits when it sees another molecule. So when a water runs into a sodium chloride, or when a carbon dioxide shows up around glucose, that's how they interact. They would have an intermolecular force. This could even be a water around another water. That's fine. As long as it's two separate molecules, we can have an intermolecular force. We just need two separate molecules already put together. So an intermolecular force is not the kind of thing that holds molecules together or that binds something together. This is just kind of like a force of interaction. This is just a way that molecules behave when they're in the same space. We're going to be concentrating or starting with a type of intermolecular force called a dipole-dipole interaction. So first, you need to understand what a dipole is. Di is two, and a pole means that we're talking about a region of electronegativity difference. So for example, if we look at the drawing that's on your slide right here between chlorine and hydrogen, if we have chlorine interacting with hydrogen, chlorine is the more electronegative atom, so it pulls the electrons over near it. And because the electrons are being pulled over to chlorine, that makes chlorine what we call partially negative. So this little guy right here, this little like bent music note, okay, a music note that went through the washing machine, or an infinity sign that isn't quite finished, it means partial. That's a sigma, okay? And actually, usually you see them drawn like that, like they look more like a bomb that's gonna go off. But I draw them like this, a partial negative charge. And what this is going to do is this means that chlorine over here is a little bit negative. And so this kind of means a little bit, okay? It's a partial. So chlorine is now a little bit negative, and that makes hydrogen, because it's kind of lost an electron, that makes hydrogen a little bit positive. And so we end up with this little bit positive, little bit negative behavior in the molecule, and that allows them to attract other positive and negative regions on other molecules around them. So the dipole is just the existence of this negative here and this positive here makes the dipole. Okay, that's called the dipole, two different regions of electronegativity. So a dipole-dipole interaction is when the dipoles of one molecule interact with the dipoles on another molecule. So let's look at what that looks like. So we're going to stick with our example of HCl here. And so what we're going to see is if I put this in a sea of other HCl's, so I'm just going to draw it like a little rectangle, and we know that this side is positive because of the hydrogen, and this side is negative because of the chlorine. In our dipole-dipole interaction, what we're going to see is that these positive and negatives, and I'm going to stop drawing the H and the Cl on the inside, I'm just going to draw the outside, right, that looks like a little pill, and we see that the negatives are going to kind of line up so that they are attracting the positives, opposites attract. And then over here, then we would see another one line up, and we would have attractions here and attractions there. And if for some reason we had another one here that was negative and positive, these would repel it and they would flip it around until it was instead positive and negative, so that we could have our stable interactions. So this dipole-dipole interaction is just this like kind of very small interaction that holds like a liquid together. And so this is the kind of thing that would keep liquid in a puddle instead of running all over the cement. Lots of molecules, lots of liquids have these dipole-dipole interactions, and these are considered to be the middle strength intermolecular force. So I'm going to put dipole-dipole right here as a middle strength interaction. And we're going to go, this is strong over here, and this is the dipole-dipole interaction is in the middle in terms of our intermolecular forces. So what we're going to do now is we're going to look at what does it look like if we make a really, really, really strong dipole-dipole interaction. How can we make the dipole interaction even stronger? And so we're going to look at a very special case of that, which is called a hydrogen bond. So a hydrogen bond is what we're going to be talking about right now. And hydrogen bonding is like a dipole-dipole turned way up. It's a special case of a dipole-dipole interaction that gets very, very strong. And so in a hydrogen bond, what we see is that the bond that is exhibiting the dipole is between hydrogen and some other very electronegative atom, like oxygen, forming water. So we're going to look at this example specifically by looking at water and how water behaves. So water is, as you know, H2O. And the structure of water looks like this. Oxygen has 6 valence electrons. So we put 6, 1, 2, 3, 4, 5, 6 valence electrons. And then we put our water, our hydrogens on here and form our bonds like this. But in real life, okay, the way that this looks is that actually the lone pairs are going to hang out together. So we can redraw this. Oxygen has its 2 lone pairs over here, and it has its 2 bonds to hydrogen, like this. And this is called a bent shape, and we don't really get into shapes in this level of chemistry, but this is called a bent shape, and it's putting its electrons, right, all of its negative electrons are over together. And then on top of that, oxygen is a really electronegative atom, and so it's winning in that tug of war, it's winning the electrons over to itself. So this area over here is partially negative, and each of our hydrogens then gets a partial positive charge on it. And so what we see now, what happens next, is that the negatives of this oxygen and the positives of the hydrogen are so strong that they're almost as strong as a cation or an anion. And so we're going to get, between this water molecule and the water molecule next to it, we're going to get a force of attraction between the positives and negatives that is so strong that it's almost as strong as an ionic bond. So we're going to get another water molecule over here. And just like with dipole-dipole, it's going to arrange itself so that the partial positive regions are near the partial negative regions. And we're going to get this attraction right here between the lone pairs on oxygen and the hydrogens. And the same thing is going to happen here. We're going to get this attraction between this partially negative lone pair on oxygen and the hydrogen. And this is going to repeat itself over and over again. And this is called a hydrogen bond. And it's a weird term because what's stronger than a hydrogen bond is an ionic or a covalent bond. A hydrogen bond is not really a bond, it's an intermolecular force. But it's so strong that it's kind of given the reverence called a bond, kind of like conferring a degree on someone, like you're an honorary PhD or you're an honorary graduate of this school. It's not really a bond, but it's so very strong that it starts to behave and have qualities similar to bonding pairs of ions. This causes a lot of the behaviors of water that we know and love. So water has a super high boiling point, which is what keeps our earth so very calm and collected, because water won't just boil away, because these intermolecular forces are hard to break, and so it keeps water a liquid at room temperature. We also see things like water has surface tension, which is important in things like water striders and allowing water to travel up tree trunks. That water floats as a solid instead of sinks. It is less dense as a solid than as a liquid, which allows for life on Earth to continue through the winter, so all of our plants and animals don't die in lakes and rivers in the wintertime. And we will dive into all of the amazing properties of water when we get to solutions next semester. But for now, we just need to understand that there is this type of bond called a hydrogen bond, and it is quite strong, and it is vitally important to your life. When it's one of those weird things, right, where this little interaction between this partially negative lone pair on oxygen and this partially positive hydrogen allows for your life to continue. This tiny little set of dots right here. So even though, we're intro level chemistry, and even though solutions isn't for a while, it's just really important that we start to get the gravity, start to understand the importance of even these little tiny dipole-dipole or hydrogen bond interactions. So this is just a type of dipole-dipole bond that is even stronger, and we call that the hydrogen bond. We typically see it in molecules like H2O and HCl and HF and H2S, but for us, we're mostly going to see it in H2O in water. The last type of interaction we have, we're going to go the other way now, back to dipole-dipole with just their positive and negative, and then we're going to take it even weaker, and we're going to ask ourselves, what could even matter at that weakness? But we're going to take dipole-dipole even weaker, and we're going to look at what happens when non-polar molecules just get knocked out of balance for a minute. So what we're looking at now is called a London dispersion or a van der Waals interaction. A van der Waals interaction is a very, very weak intermolecular force. So weak that we call it sometimes a dipole moment. So what's happening in van der Waals is just imagine yourself in a crowded place. Okay, maybe you're waiting for a parade at Disneyland, or you're waiting for a concert to start and you're standing in the pit. Don't all these things sound great? You're standing in line for something somewhere crowded because the world is open again because COVID, it's before or it's after. There's going to be lots of times when we do this, but maybe not this weekend. So you're standing in this very crowded place, and everyone tends to stand in a crowd with an appropriate amount of personal space. So they stand, I mean, imagine you wouldn't like go stand in line. It's just funny to me to think of doing this. But if you like walked in line, like you're in line for Space Mountain, and you just walked all the way up to the person in front of you in line till you were touching them, like till you just went like, just so that your arms were touching their arms and you just stood there to the stranger, okay? They would move, right? They're gonna shift. So if you get too close to them, they're gonna feel that you've encroached on their personal space and they're gonna shift over, okay? And so where you were kind of evenly spread, now your movement causes their movement, and then as they move then closer to the person sitting next to them, that person might in turn shift and move a little bit over, and so on and so forth. And maybe you cause this like huge domino effect all the way to the point where the person in the front of the line steps over the yellow line, oh my gosh, and then gets hit by and then they get in trouble. No one cares. Anyway, they step over the yellow line, the do not cross line, and you have created this huge chain reaction from your just encroaching on the personal space of the person in front of you. That kind of cumulative response is what we're looking at when we're looking at van der Waals. So you can see, and I'm actually going to use the diagram that's here because it's pretty good. So we can see two different molecules. So let's say these are chlorine Cl2s. Okay, this is chlorine with chlorine. And so they have this kind of green cloud around them. Remember, the green cloud means that we have even electron share. And there's another one right here next to it, and it has even electron share. And then for some reason, this is kind of just random chance. Remember, electrons are moving really, really fast, and they can go really anywhere they want. So for some reason, we get a quick shift where we get a lot of electrons over here in this blue region, and we get a little electron missing over here, and we get this positive charge for a moment. Well, this positive charge is going to attract electrons, right? Because opposites attract, and so the positive charge attracts the negative electron of the neighbor. It's going to attract the electron over to it. So the electron then is going to travel over here, and that's going to create a negative charge over here with a positive charge over there. And this is going to quickly like ripple through like dominoes, okay? So we're going to get this like ripple through, and then it will reset, okay? Everyone moves forward, but then they move back to their original position. They just get knocked off balance and then they reestablish. And it feels like it's nothing. Like, what would that ever do? But this kind of a van der Waals interaction, which is a slight shift of the electron, which creates a temporary dipole, or what we call a dipole moment, which then affects the next molecule next to it, and so on and so on. This is responsible for geckos being able to climb up a wall. They actually utilize dipole moments to get that stickiness on their feet to allow them to move like that. They're creating a dipole shift in a surface that is otherwise not magnetic. They're able to create this kind of light dipole shift. It's very similar, like in my mind, it works kind of like crowd surfing. Okay, the idea that no one is really like holding you and carrying you around, but when everyone's arms go up and they all kind of put a little bit of work into it, then you're able to get moved around. Many hands make light work. That's the old adage, and that's kind of the idea of the van der Waals, that the cumulative effect of all of these tiny shifts really can cause large impacts in a chemical system. This is showing you the average shape, the temporary shift, and then that temporary shift affects other molecules. So at this point, we have done so much work, you guys. I'm so proud of you. Okay, so we have looked at chemical bonds, and specifically at covalent chemical bonds, which remember is the sharing, not sharing, fighting over electrons. And we can either have an even share in a non-polar covalent bond or an uneven share in a polar covalent bond. And then once we've formed polar covalent bonds, we can see a dipole-dipole or a hydrogen bond, okay, in our polar bonds, or in our non-polar bonds, we can see that van der Waals or London dispersion interaction that gives us just that dipole moment, that temporary shift, and the larger cumulative effect. So all that's left to do is look at these ionic bonds And then we'll wrap up with a little comparison between ionic covalent. And finally, we'll talk just quickly about something called a metallic bond because they're interesting and applicable to our lives. And then you'll be all done with semester 1 of chemistry. So good job, you guys.